Here's what you're about to find out. How engineers locate a break miles underwater. What really happens inside a deep-sea repair ship. Why most cable failures happen in the shallowest water, and how close the world came to losing underwater cables altogether. Right now, 99% of all international internet traffic is moving through cables on the ocean floor. Not satellites, not radio waves, cables. Around 1.3 million kilometers of them, in places as thin as a garden hose, laid across some of the deepest water on Earth. When one breaks, which happens roughly 200 times a year, someone has to go down and fix it. The modern internet feels invisible. We think of it as clouds, wireless signals, something floating above us. The reality is almost absurdly physical. Every message sent across an ocean travels as pulses of light through glass fibers no thicker than a human hair, wrapped in steel and polyethylene and resting on the seabed thousands of meters down. These cables carry financial transactions, video calls, government communications, and medical data. On a busy day, a single major cable system can move around 200 terabits per second. When one goes dark, it does not just slow streaming. It can disconnect entire countries from the global economy. In 2008, when two cables snapped near Alexandria, Egypt lost about 70% of its international internet capacity overnight. So how do you repair something sitting at the bottom of the ocean? The answer is a small and unusual fleet of specialized ships. Fewer than 60 are in service worldwide. Their crews handle one of the most demanding repair jobs in modern engineering. The tools they use look partly medieval and partly futuristic. And behind all of it sits a deeper concern. This infrastructure is mostly privately owned, largely invisible, and more fragile than most people realize. To understand how repairs happen, you first need to understand what these cables are, where they go, and why they break. The causes range from the ordinary to the extreme. A fishing trawler dragging gear, an anchor dropped in the wrong place, an underwater earthquake that reshapes the seafloor while the cable runs across it. The first submarine telegraph cable crossed the Atlantic in 1858 after years of failed attempts and huge expense. It worked only briefly before the signal died because the engineers had pushed too much voltage through the line. The insulation failed, but the core idea was proven. Continents could be linked through the ocean floor. That first cable was crude by modern standards, but it established the basic ambition. Once people realized a line on the seabed could carry information, the next century became a race to make that line faster, more durable, and less expensive to keep alive. By the 1950s and 1960s, telephone cables were crossing the Atlantic and Pacific. They were thicker, better insulated, and carried voice rather than Morse code. The repair methods developed then, grappling hooks, surface ships, and specialized splicing, became the foundation for everything that followed. A modern submarine cable is a carefully engineered sandwich. At the center are optical fibers, each carrying separate channels of light. Around them sits a steel strength member that carries the mechanical load. Then comes copper for powering signal repeaters. After that are waterproofing layers, another steel armor layer, and an outer polyethylene sheath. The repeaters are critical. Light loses strength over distance, so every 60 to 100 kilometers, the cable contains a repeater, a sealed titanium unit that boosts the signal and passes it onward. A single transoceanic cable can contain more than 150 of them. They are powered by direct current sent from shore stations at both ends. Those repeaters are what make the modern internet truly global. Without them, the light would decay too quickly across a long ocean span. They are small compared with the cable itself, but they are the reason a signal can cross thousands of kilometers without dying. In shallow coastal waters, usually anything above about 1,500 meters, cables are buried under the seabed for protection. Cable ships tow specialized plows that cut a trench, lay the cable, and backfill it in one pass. This is where a large share of the damage happens. Shallow water means fishing fleets, anchors, and shipping traffic. In the deep ocean, the cable usually lies unburied on the bottom. The burial depth is often only a meter or so, but that is enough to protect the cable from ordinary seabed activity. The problem is that coastal waters are exactly where people and ships are most concentrated, which makes the shallowest portions of the network the most vulnerable. When a cable breaks, the first clue comes from the network itself. Monitoring stations watch the traffic flowing through the system. If a segment goes dark, alarms trigger within seconds. But knowing a cable is broken and knowing exactly where it is broken are very different problems. Fault location starts with optical time domain reflectometry. Engineers send a pulse of light into the cable from shore. The light travels until it hits the break, then some of it reflects back. By measuring the round-trip time, they calculate the fault distance. On a deep ocean cable, that distance may be thousands of kilometers from shore. The measurement is not exact. Light speed through glass changes slightly with temperature and pressure. The cable route bends with the seafloor and can be 10% to 20% longer than the straight line estimate. So the result is a search window, not a point. That window may still cover 10 or 15 kilometers of ocean floor. Once the search area is established, a repair ship is sent out. These vessels are rare and expensive. A cable ship can cost about $50 million to build and carry a crew of around 60 specialists. They sail at roughly 12 knots. In the Atlantic, a ship may need 4 or 5 days just to reach the fault zone. All that time, the cable remains down. On the way, the crew prepares. The ship carries spare cable, sometimes hundreds of kilometers of it, stored in large tanks filled with seawater so the cable stays cool and flexible. It also carries grapnels, remotely operated vehicles, and splicing gear precise enough to join glass fibers thinner than a hair. The ROVs are remarkable machines. They descend on umbilical cables that can reach 6,000 meters. At that depth, pressure is around 600 atmospheres, enough to crush a car. The vehicles carry cameras, sonar, manipulator arms, and water jetting tools. They can search for a cable buried under sediment centimeter by centimeter. The work is part engineering, part ocean exploration. The repair team has to deal with currents, visibility, temperature, and navigation, while also managing a delicate instrument that cannot be jolted or kinked. A cable on the seabed is both a utility line and a fragile precision product. When the ship reaches the fault window, the search begins. In shallower water, under about 2,000 meters, the crew may use a grapnel, a heavy multi-pronged hook dragged across the seabed on a long wire. The logic is simple. Drag until the cable catches, then haul it up. In practice, you're dragging a hook across a dark, featureless plane, trying to snag something the width of a wrist. In deeper water, grapnels become less effective. The wire required to reach the bottom becomes too heavy and hard to handle from the surface. That is where the ROVs take over. They map the seafloor with sonar, spot the faint line of the cable in the sediment, and move in slowly with cameras to confirm it visually. Finding the cable is only the first challenge. The next is figuring out what happened to it. Sometimes the break is clean, with two ends sitting close together on the bottom. Sometimes the damage stretches over kilometers, with sections abraded, kinked, or buried by a fresh debris slide. Each situation calls for a different repair strategy. Shallow coastal zones are where most faults actually happen, because shallow water means people. A trawler in the North Sea can drag a net across a cable and sever it without even noticing. A container ship dropping anchor in a crowded harbor can cut through several cables at once. The waters near Taiwan, one of the busiest cable corridors in the world, see repeated incidents every year. Submarine landslides are another serious threat. When sediment on a steep underwater slope collapses, it can carry a cable kilometers away from where it was laid and bury it under meters of debris. The 2006 Hengchun earthquake near Taiwan triggered exactly that kind of damage. 7 cables were affected at once, and restoring service took 49 ship days of work and 11 weeks. Once the fault has been confirmed and the damage assessed, the repair can begin. For a relatively shallow break, the grapnel or ROV brings up the damage section. The crew cuts out the bad portion and leaves 2 cable ends hanging over the side of the ship. Then the real precision work starts, joining optical fibers that are only 125 micrometers wide. Fiber splicing is done with a fusion splicer, a machine that uses an electric arc to melt 2 fiber ends together at the molecular level. Before that, the fibers must be cleaved with a diamond blade to create a flat face accurate to a fraction of a micrometer. The splicer aligns the ends with cameras and motors, then fires the arc. The whole process takes less than a minute per fiber. Each splice is tested immediately. Engineers at shore send light pulses through and check the return signal. A good splice loses almost no strength. A bad one reflects too much light and has to be redone. On a cable with many fiber pairs, the process is repeated for every strand before the joint housing is sealed. If the damaged section was long, the crew inserts a fresh length of cable between the two recovered ends. That creates two splice joints instead of one. It also creates another issue. The replacement cable is longer than the section it replaces. The extra length has to go somewhere, so it is looped on the seabed. That loop stays there permanently, a quiet artifact of the repair. Now imagine doing all of that while the ship is moving on ocean swells. On a calm day in mid-Atlantic weather, the sea may be manageable, but cable breaks do not wait for calm weather. Repairs have been carried out in 4-meter swells with the deck pitching and the cable swinging in the air. The work demands intense focus, and it does not get easier when conditions worsen. Somewhere off the mid-Atlantic ridge, a ship may be on station for days. The weather turns. The deck rises and falls. The cable comes over the stern roller slick with seawater, and the crew guides it by hand. Inside the splice workshop, the air smells of solder and machine oil. The fusion splicer sits bolted to the bench, steady even as the hull groans. A technician works over fiber ends no bigger than a ballpoint pen tip. Outside, wind and spray. Inside, silence except for the soft beep confirming each junction has sealed. When the final splice passes its test, the ship begins to pay out the cable back into the sea. It descends slowly, disappearing into dark water. At 4,000 meters, pressure will compress the joint housing until the steel bites tight. The repair is finished, but the system is not live until shore stations confirm the link is restored. The crew waits. The ocean does not care. A typical deep-water repair takes 4 to 10 days from fault detection to restored service. Shallow faults near coastlines can take longer because the ship must work around shipping traffic, permits, and local authorities. A repair off the coast of West Africa may require approvals from several governments before the ship can even start. The cost of a single repair is usually between $1 million and $3 million, not counting the economic damage caused by the outage itself. Repair contracts are pre-arranged. Cable owners pay annual maintenance fees to a small number of companies that operate the repair fleets. The largest names in that business cover most of the oceans. They are the companies that own the ships, train the crews, and keep the spares ready. Yet some regions are still poorly protected. The Pacific has relatively strong coverage, but parts of sub-Saharan Africa, some island nations, and remote territories often rely on 1 or 2 cables and almost no backup. When those lines break, a repair ship may be many sailing days away. There's also the question of deliberate damage. Sabotage of submarine infrastructure has become a real concern because these cables pass through the same waters as pipelines, shipping lanes, and military choke points. Some routes run through narrow corridors such as the Strait of Malacca, the Red Sea, and the Luzon Strait, where they are especially exposed. That is why defenders talk less about absolute protection and more about redundancy. If enough parallel routes exist, losing one cable changes little. New systems are being built at a faster pace than at almost any other point in history. Some new routes link South America and Africa. Others circle the African coast or avoid the most vulnerable choke points. These cables carry more capacity and are designed to spread risk more effectively. Meanwhile, the repair fleet itself is aging. Some ships still in service were built in the 1990s. Finding enough engineers and splice technicians is an ongoing challenge. The skills are highly specialized, working with optical fiber in marine conditions, operating ROVs at depth, navigating territorial waters, and solving problems under pressure. It takes years to build that expertise. What makes this story worth sitting with is the gap between what the internet feels like and what it actually is. It feels instant and frictionless. The reality is a physical network laid by hand across ocean floors, maintained by a few thousand specialists on a few dozen ships, and repaired with tools that include diamond blades and grappling hooks. The next time a video call drops or a website slows down, the cause might be a fishing anchor 1,000 meters down in the North Sea. And the fix might be a ship already days out from port, carrying spare cable and a crew that knows how to do one of the rarest jobs in the world. The whole internet rests on that. That is why redundancy matters so much. A global network is only as strong as the number of alternate paths it has when one line fails. Extra routes, spare capacity, and maintenance ships are what turn a fragile chain of glass into something the world can actually rely on.